After the mass extinction of dinosaurs 66 million years ago, the Cretaceous-Paleogene extinction event, Earth turned into a post-apocalyptic world where surviving species fought for their place under the sun. But before we dive into how this happened, don't forget to like and subscribe. So my dear viewer, here's what it looked like. The first hours to years after the dinosaur-killing impact. A planet in agony the moment the Chicxulub asteroid struck Earth 66 million years ago, marked the beginning of the most violent day in our planet's history. This mountain-sized space rock, approximately 10 kilometers, 6 miles in diameter, and weighing an estimated 2 trillion tons, slammed into what is now Mexico's Yucatan Peninsula with an energy release equivalent to 100 trillion tons of TNT. To comprehend this staggering force, consider that it equals about 2 million of the most powerful nuclear weapons ever detonated, all concentrated in a single instantaneous event. The physics of this collision were so extreme that they temporarily altered fundamental properties of matter at the impact site. As the asteroid punched through the atmosphere in less than a second, it compressed the air ahead of it to such density that the normally transparent atmosphere became incandescent plasma, glowing hotter than the sun's surface before physical contact even occurred. When impact happened, the kinetic energy release vaporized both the asteroid and approximately 100 cubic kilometers of Earth's crust within milliseconds. The initial shock front propagated through the crust at speeds exceeding 20 kilometers per second, 45,000 miles per hour, creating a temporary cavity 30 kilometers 18 miles deep and 80 kilometers 50 miles wide. Within 3 minutes, this cavity collapsed upward in a colossal rebound that formed a central peak higher than Mount Everest before collapsing again to form the final crater structure we see today in seismic surveys. The seismic waves generated by this event were beyond anything recorded in human history. Modern modeling suggests they would have registered between magnitude 11 and 12 on the Richter scale, making every earthquake in recorded history seem insignificant by comparison. These shockwaves traveled through the entire planet, triggering secondary earthquakes and volcanic eruptions worldwide that may have persisted for months. The thermal effects were equally apocalyptic. Within microseconds of impact, temperatures at ground zero exceeded 20,000 degrees Celsius, 36,000 degrees Fahrenheit, hot enough to vaporize solid rock. This created an expanding fireball that raced outward at hypersonic speeds, superheating the atmosphere to oven-like temperatures across continents. Paleontologists have found charred dinosaur fossils in Montana's Hell Creek Formation, some 3,000 kilometers, 1,800 miles from the impact site, showing burn patterns consistent with exposure to 500 degrees Celsius, 932 degrees Fahrenheit heat for several minutes. The thermal pulse likely ignited wildfires across most of North and South America within hours, with soot and ash from these fires later found in sediment cores worldwide. Computer models suggest the radiant heat was intense enough to spontaneously ignite dry vegetation up to 5,000 kilometers, 3,100 miles, from ground zero, effectively setting fire to most of the Western Hemisphere within a single day. The marine consequences were equally catastrophic. The impact displaced approximately 100,000 cubic kilometers of water, equivalent to 3 times the volume of the modern Baltic Sea. This generated tsunamis with initial wave heights approaching 1.5 kilometers, 0.9 miles, near the impact site. Even after traveling across the entire Gulf of Mexico, these waves would have still been 100 to 300 meters, 330 to 1,000 feet, high when they reached coastal areas. Sediment cores from Texas to Florida show multiple layers of disturbed deposits, each representing successive waves scouring the continental shelf. In some locations, these deposits contain marine microfossils mixed with terrestrial material and impact debris, demonstrating how the waves completely reshaped coastlines. The energy was so immense that it created Sichi waves in inland seas and lakes worldwide. Paleolimnological studies show even freshwater systems in Asia and Europe experienced dramatic sediment disturbances at this time. The atmospheric effects became global within days. The impact vaporized sulfate-rich sedimentary rocks, injecting approximately 325 billion metric tons of sulfur dioxide directly into the stratosphere. This sulfur combined with water vapor to form reflective sulfate aerosols that spread across the planet within weeks. Climate models suggest these aerosols reduced sunlight reaching Earth's surface by 80 to 90% for at least a year, with significant dimming persisting for nearly a decade. The resulting impact winter saw global average temperatures plummet by 25 degrees Celsius, 45 degrees Fahrenheit, a drop that would make even tropical regions experience freezing temperatures year-round. Recent studies of leaf wax biomarkers from this period showed dramatic changes in precipitation patterns, with some areas becoming arid while others experienced intense acid rainfall. The chemical consequences reshaped Earth's surface chemistry. The sulfur-rich atmosphere produced acid rain with pH levels as low as 4.0, comparable to lemon juice. In the oceans, this caused a sudden pH drop of 0.3 to 0.5 units, triggering carbonate dissolution that particularly affected organisms with calcium carbonate shells or skeletons. Paleontological studies show that over 90% of planktonic foraminifera species, the base of marine food chains, went extinct within months. On land, acid deposition poisoned freshwater systems and damaged plant foliage, compounding the effects of darkness and cold. Geochemical analysis of KPG boundary clays reveals elevated concentrations of heavy metals like chromium and arsenic, leached from impacted rocks and distributed globally through the atmosphere. The fossil record preserves dramatic evidence of this global catastrophe. The famous KPG boundary layer, identifiable worldwide in both marine and terrestrial sediments, contains multiple diagnostic signatures. A spike in iridium concentrations indicating extraterrestrial material, shocked quartz grains showing planar deformation features from the immense pressure, microtectites, and a distinct fern spike showing how pioneer plants colonized the devastated landscape. Palynological studies reveal that fungal spores dominate immediately above the boundary, outnumbering plant pollen by factors of 100 to 1 in some locations, clear evidence of decomposers thriving on the massive die-off of other life. Remarkably, some organisms survived this apocalypse through a combination of luck and specialized adaptations. Small mammals like the early primate relative Purgatorius persisted because their burrowing habits provided shelter from the worst surface conditions. Crocodilians and turtles survived thanks to their slow metabolisms and ability to go months without food. Examination of growth rings in turtle shells from this period shows years of stunted growth followed by recovery. Certain fish species found refuge in deep or sheltered aquatic environments. Isotopic analysis of their teeth shows abrupt dietary shifts corresponding to the collapse of marine food webs. Even some birds made it through, their hollow bones and high metabolisms proving advantageous in the chaotic aftermath. The Chicxulub impact didn't just end the age of dinosaurs, it fundamentally rewrote Earth's evolutionary playbook. The mass extinction created ecological opportunities that allowed mammals to diversify from tiny insectivores into the dominant terrestrial vertebrates. This single catastrophic event, lasting mere minutes in its initial phase but with effects persisting for millennia, altered the course of biological history in ways we're still unraveling today. The geological and paleontological evidence preserved in rocks worldwide continues to tell this story of destruction and renewal, one of the most pivotal chapters in our planet's 4.5 billion year history, and without which humans would never have evolved to contemplate it. The impact demonstrates with brutal clarity how random cosmic events can redirect the trajectory of life, wiping out evolutionary dynasties in an instant while creating opportunities for new forms to emerge from the ashes. The first centuries. The age of mushrooms and rats. The first centuries following the catastrophic asteroid impact that wiped out the dinosaurs represented one of the most profound ecological transformations in Earth's history. As the skies remained choked with fine particulate matter from the impact, sunlight penetration was reduced to just 1 to 2% of normal levels for several years, creating conditions similar to perpetual twilight across the globe. This dramatic reduction in solar radiation triggered a cascade of ecological collapses that fundamentally reshaped terrestrial and marine ecosystems. The lush, dinosaur-dominated forests that had thrived during the Cretaceous period withered and died en masse, their towering conifers and flowering plants unable to photosynthesize in the dim ashen light. Paleobotanical studies of pollen and spore records from this period show an abrupt disappearance of diverse plant communities, replaced initially by vast stretches of decaying vegetation, and later by hardy pioneer species that could survive in the harsh post-impact environment. The collapse of plant life had immediate and devastating consequences for herbivores. Large dinosaurs like the hadrosaurs and ceratopsians that had dominated Cretaceous landscapes starved within months of the impact, their massive bodies requiring more food than the devastated ecosystems could provide. Isotopic analysis of fossil bones from the KPG boundary reveals telltale signs of starvation stress in the last surviving dinosaurs. As the herbivores perished, the carnivores that depended on them soon followed. Tyrannosaurs and other large predators found themselves without prey in a world where even carrion became scarce. The fossil record shows this trophic collapse occurring with remarkable speed, with most large vertebrate species disappearing within a few decades of the impact event. In this strange new world, the ecological balance shifted dramatically toward decomposers. Fungi, particularly species like Trichoderma and other S-apotrophic forms, flourished in the unprecedented abundance of dead organic matter. Paleontologists have identified a distinct fungal spike in sediment layers dating to this period, a sudden increase in fungal spores that outnumbers plant pollen by factors of 100 to 1 in some samples. These fungal networks became the dominant life forms across vast stretches of the planet, breaking down the immense quantities of dead vegetation and animal matter that covered the landscape. Some estimates suggest fungal biomass may have temporarily exceeded that of all surviving plants and animals combined during this period. The efficiency of these decomposers was crucial in recycling nutrients back into the devastated ecosystems, setting the stage for eventual recovery. The animal survivors of this apocalypse shared several key characteristics that enabled their persistence through the worst environmental conditions Earth had experienced in hundreds of millions of years. Mammals like Purgatorius, a primitive primate ancestor no larger than a modern rat, possessed a combination of traits that proved invaluable in the post-impact world. Their small body size required relatively little food compared to dinosaurs. Their endothermic metabolism allowed them to remain active in the cooling climate, and their generalist diets meant they could subsist on whatever organic material remained, from insects to seeds to fungi. Perhaps most importantly, many of these early mammals were burrowers or could utilize underground shelters, protecting them from the worst surface conditions. Dental microwear analysis of Purgatorius fossils shows wear patterns consistent with a highly varied diet, suggesting these adaptable creatures could shift their feeding strategies as different food sources became available or scarce. Birds, as the last surviving lineage of dinosaurs, demonstrated remarkable resilience in the face of the catastrophe. Their evolutionary innovations, feathers for insulation, efficient respiratory systems, and in many cases small body sizes, gave them distinct advantages over their extinct dinosaur relatives. Some paleontologists estimate that up to 80% of bird species perished in the extinction event, but those that survived tended to share certain characteristics. Many were ground-dwelling species capable of flight, allowing them to search widely for scattered food sources. Others were seed-eaters, able to exploit this durable food source that could remain viable for years after the impact. Isotopic studies of bird fossils from immediately after the extinction show carbon signatures indicating many survived by feeding on the abundant insects that thrived on decaying matter, particularly wood-boring beetles that proliferated in the dead forests. Reptiles exhibited different but equally effective survival strategies. Crocodilians and turtles, which persisted through the extinction event, benefited from their ectothermic metabolisms that required less food than similarly sized endotherms. Modern crocodiles can survive for months without eating, and their Cretaceous ancestors likely had similar capabilities. Additionally, many of these reptiles were semi-aquatic, potentially finding refuge in water bodies that may have provided more stable microclimates than the dramatically fluctuating terrestrial environments. Examination of growth rings in turtle shells from the KPG boundary shows evidence of slowed growth rates consistent with extended periods of food scarcity and environmental stress. The marine environment, while somewhat buffered from the initial thermal effects of the impact, suffered its own devastating transformations. The collapse of photosynthetic plankton communities due to reduced sunlight caused the marine food web to crumble from its base upward. Larger marine reptiles like mosasaurs and plesiosaurs, which depended on robust food chains, quickly disappeared. However, some fish species survived, particularly those adapted to low-oxygen environments, or those capable of subsisting on detritus and microbial mats. Deep-sea ecosystems which rely less on surface productivity and more on chemosynthetic processes were largely unaffected, preserving lineages that would eventually recolonize shallower waters. The chemical environment of the post-impact world presented additional challenges. Continued acid rain, with pH levels as low as 4.0 in some regions, leached nutrients from soils and made many freshwater systems inhospitable to sensitive organisms. Atmospheric chemistry studies based on ice core proxies from later periods suggest that toxic gases like sulfur dioxide and nitrogen oxides remained elevated for decades, potentially causing respiratory stress for air-breathing animals. The oceans experienced prolonged acidification as the sulfate aerosols gradually washed out of the atmosphere, with carbonate chemistry remaining disturbed for perhaps thousands of years, a geological instant but an eternity for surviving organisms. Climate instability characterized this entire period. Without the moderating influence of extensive vegetation cover, temperature swings became more extreme. Computer models suggest daily fluctuations may have exceeded 20 degrees Celsius, 36 degrees Fahrenheit, in some continental interiors, with nights plunging below freezing even as daytime temperatures rose significantly. The loss of forest cover also altered precipitation patterns, with some regions becoming much drier while others experienced intense seasonal rains. These erratic conditions placed additional stress on surviving ecosystems, favoring generalists over specialists and contributing to the relatively low biodiversity that persisted for millennia after the impact. The survivors existed in a world utterly transformed from the lush, dinosaur-dominated ecosystems of the Cretaceous. Atmospheric dust and aerosols created perpetual dim light conditions for years, with optical depth measurements from sediment samples suggesting the sun would have appeared as just a faint disk in the sky. The air carried a constant metallic tang from impact debris and volcanic emissions, while the ground was covered in a layer of fine ash that choked waterways and buried organic matter. In this harsh environment, every day was a struggle for existence, with organisms pushed to the absolute limits of their physiological tolerance. Yet from this devastation emerged the seeds of Earth's ecological future. The small mammals, birds, and reptiles that survived would become the founders of new evolutionary lineages. Their adaptations, the ability to endure hunger, to exploit varied food sources, to shelter from environmental extremes, would prove invaluable in the coming millennia as ecosystems slowly recovered. The age of dinosaurian giants had ended, but in their absence, new forms of life would eventually flourish, setting the stage for the rise of mammals and ultimately the appearance of humans. This period of survival against all odds represents one of the most critical chapters in our planet's history, demonstrating both the fragility and resilience of life in the face of catastrophic change. The fossil record preserves this dramatic transition, a testament to life's ability to endure even the most extreme challenges and eventually thrive again under new circumstances. After 100,000 years, the Fern Age, Earth's first recovery after the apocalypse. 100,000 years after the Chicxulub asteroid impact, Earth's ecosystems began their first tentative steps toward recovery. Though the planet that emerged bore little resemblance to the lush, dinosaur-dominated world that existed before the catastrophe. The thick clouds of dust and aerosols that had blocked sunlight for years had finally settled, allowing solar radiation to penetrate the atmosphere once more. But the landscape remained fundamentally transformed. Vast stretches of continental interiors were now covered in sprawling fields of ferns, their simple vascular systems and ability to reproduce via spores making them uniquely suited to colonize the still disturbed soils. These pioneer plants formed dense, low-lying carpets across terrain that had once supported towering forests, their rhizomes slowly working to stabilize the ravaged topsoil and rebuild nutrient cycles. The dominance of ferns during this period is clearly recorded in the fossil record through palynological studies, which show an overwhelming abundance of fern spores in sediment layers dating to this time, a phenomenon paleobotanists refer to as the fern spike. What makes this floral revolution particularly remarkable is that these weren't the same species of ferns that had existed during the Cretaceous. Instead, they represented a new wave of specially adapted varieties that evolved to thrive in the post-impact environment. Their leaves often showed thicker cuticles and other xeromorphic adaptations, suggesting they were coping with elevated UV radiation and possibly still fluctuating moisture levels. As these fern prairies expanded, they created new ecological opportunities that were quickly exploited by surviving animal lineages. Snakes, which had been relatively minor components of Cretaceous ecosystems, underwent an extraordinary evolutionary radiation. Freed from predation pressure by the disappearance of large theropods, and with an abundance of small prey available, early snake species diversified into a variety of new forms. Some paleontologists estimate that nearly 80% of modern snake lineages originated during this post-impact period. Fossil evidence from Montana's Hell Creek Formation shows snakes rapidly increasing in both size and diversity, with some species like the extinct Sanage reaching lengths of 3.5 meters and developing specialized constricting abilities to subdue prey. Their ectothermic metabolisms proved particularly advantageous in an environment where food supplies remained unpredictable, allowing them to survive on just a few large meals per year. Wetland ecosystems became hotspots of biological activity during the Fern Age. The altered precipitation patterns and changed topography from the impact created extensive new marshlands and floodplains, providing ideal habitats for amphibians to stage their comeback. Frogs and salamanders, which had existed in the shadow of dinosaurs for millions of years, suddenly found themselves as dominant vertebrates in many freshwater environments. Fossil beds from this period show an explosion in amphibian diversity, with some species like the giant Beelzebufo, a frog with a skull width of 15 centimeters, reaching sizes unimaginable in today's ecosystems. Their permeable skin, once a liability in the toxic post-impact environment, became an advantage as it allowed for efficient gas exchange in oxygen-rich waters, while their ability to estivate helped them survive periodic droughts. Perhaps the most visually striking inhabitants of the Fern Age were the giant flightless birds that began to appear around this time. Species like Gasterny, formerly known as Diatryma, stood over 2 meters tall and weighed upwards of 175 kilograms, making them the largest land animals of their era. Analysis of their beak morphology and isotopic signatures in fossilized bones suggests these massive birds filled herbivorous niches similar to those once occupied by hadrosaurs and ceratopsians, though some researchers speculate they may have also been opportunistic carnivores. Their evolutionary success demonstrates how quickly life rebounded. Within just a few 100,000 years, ecosystems had developed new apex consumers to replace the vanished dinosaurs. The insect world underwent its own remarkable transformations during this period. With most flowering plants still struggling to recover, many insect groups shifted to feeding on ferns, fungi, and decaying organic matter. Beetles, which had already been diverse during the Cretaceous, became even more varied, with wood-boring species playing a crucial role in breaking down the immense quantities of dead vegetation. Fossilized amber from this transitional period shows unexpected insect-fern interactions, including specialized pollinators that may have facilitated the spread of certain fern species. Flies also radiated dramatically, with many species adapting to feed on the abundant carrion or serve as parasites for the growing populations of small vertebrates. Climate conditions during the Fern Age remained highly unstable compared to pre-impact norms. While the worst of the impact winter had passed, volcanic activity triggered by the asteroid's seismic shocks continued to pump greenhouse gases into the atmosphere. This created a paradoxical situation where some regions experienced intense greenhouse warming, while others still struggled with lingering cooling effects. Oxygen isotope data from deep-sea cores indicates global temperatures fluctuated by as much as 5 to 8 degrees Celsius during this period, with particularly dramatic swings occurring over timescales of just a few centuries. Rainfall patterns were equally erratic, with evidence of both extreme droughts and catastrophic flooding events preserved in the geological record. Marine ecosystems showed parallel signs of recovery during this time. Plankton communities, which had nearly collapsed in the immediate aftermath of the impact, began to rebound as sunlight penetration improved. The fossil record shows a gradual return of calcareous nanoplankton and foraminifera, though their shells were often thinner and more fragile than their Cretaceous ancestors, suggesting ocean chemistry was still not fully stabilized. In shallow coastal areas, the first simple coral communities started to reappear, though they lacked the complexity and biodiversity of modern reef systems. These pioneer corals were mostly small, solitary forms that could tolerate the still elevated nutrient levels and variable temperatures of post-impact seas. The Fern Age represents one of evolution's most fascinating natural experiments, a complete reset of terrestrial ecosystems that allowed previously marginal groups to rise to prominence. What makes this period particularly remarkable is how quickly life rebounded once conditions stabilized slightly, with new ecological relationships forming in geological eye blinks. The ferns that dominated the landscape weren't just occupying empty space. They were actively engineering their environment, stabilizing soils, moderating microclimates, and creating habitats for other organisms. Similarly, the animals that thrived during this time weren't simply surviving. They were laying the foundations for entirely new food webs that would eventually support the rise of mammals. This 100,000-year window provides crucial insights into how ecosystems respond to catastrophic disturbances. The recovery wasn't linear or uniform. It proceeded in fits and starts, with frequent setbacks and surprising innovations. Some evolutionary experiments, like the giant birds, would eventually fade away, while others, like the snake radiation, proved enduringly successful. The Fern Age serves as a powerful reminder of life's resilience, but also of its unpredictability. When the rules change dramatically, the winners and losers can be completely unexpected. As our own planet faces rapid environmental changes, studying this ancient recovery period may provide valuable lessons about how ecosystems rebuild after catastrophe. The legacy of the Fern Age extended far beyond its relatively brief duration. The ecosystems that emerged from this period set the stage for the Paleocene-Eocene thermal maximum that would follow, and ultimately for the rise of modern mammalian-dominated biomes. Every oak forest, every tropical grassland, every alpine meadow on Earth today can trace its origins back to these humble fern prairies and their pioneering inhabitants. In a very real sense, the world we know exists because life found a way to reinvent itself during this crucial window of Earth's history, proving that even the most devastating catastrophes can ultimately give rise to new beginnings. One to 10 million years later, rise of the mammals. For 160 million years, mammals existed as Earth's perpetual understudies, small shadow-dwelling creatures that scurried through the night while dinosaurs dominated the daylight hours. Rarely exceeding the size of a modern badger, these early mammals occupied ecological niches so marginal that most dinosaur species likely never noticed their existence. Yet when the Chicxulub asteroid struck 66 million years ago, it erased the ruling reptilian dynasties in geological seconds, leaving behind an empty world ripe for reinvention. What followed was one of evolution's most spectacular creative outbursts, a 10-million-year frenzy of diversification that transformed these once insignificant creatures into the architects of a new biological order. The stage for this revolution was set by dramatic climate changes during the Paleocene and Eocene epochs. As Earth recovered from the impact winter, temperatures began climbing steadily until reaching their zenith during the Paleocene-Eocene thermal maximum, PETM, about 56 million years ago. Oxygen isotope data from deep-sea cores reveals global temperatures spiked 5 to 8 degrees Celsius, 9 to 14 degrees Fahrenheit, above modern averages, creating greenhouse conditions more extreme than anything seen since the Mesozoic. The Arctic became a subtropical paradise where winter temperatures rarely dipped below 10 degrees Celsius, 50 degrees Fahrenheit, allowing crocodiles to bask along shores that would one day freeze solid. Fossilized palm fronds and tropical ferns found in Alaska and Svalbard testify to rainforests that stretched unbroken from equator to poles, while deep ocean temperatures reached a bathtub-like 20 degrees Celsius, 68 degrees Fahrenheit at abyssal depths. This planetary sauna accelerated mammalian evolution by supercharging primary productivity. Lush vegetation supported exploding herbivore populations, which in turn fed increasingly sophisticated predators. In the steamy Paleogene forests, the first primates were making their debut. Species like Carpolestes simpsoni, no larger than a squirrel, developed revolutionary adaptations for arboreal life. Their opposable digits and nails, rather than claws, allowed precise grasping of branches, while forward-facing eyes provided the depth perception needed to leap safely through dense canopies. Analysis of inner ear fossils shows these early primates already possessed the enhanced balance systems that would later enable their descendants to perform acrobatic feats. Meanwhile, on the forest floor, rodents were undergoing their own quiet revolution. The discovery of Tribosphenemus minutus fossils in Mongolia reveals how their continuously growing, self-sharpening teeth made them masters of processing tough plant materials, an innovation that would eventually make rodents the most diverse mammal group on Earth. Predatory mammals seized their new opportunities with terrifying creativity. The Mesonychids, bizarre wolf-like creatures with hooves instead of paws, developed bone-crushing dentition that allowed them to tackle prey much larger than themselves. Recent CT scans of Oncologon skulls show bite forces exceeding 1,000 newtons, comparable to modern hyenas. Yet these terrestrial hunters held an even more surprising legacy in their genes. They were the direct ancestors of modern whales. The amphibious Pakicetus, discovered in 50-million-year-old Pakistani sediments, reveals the first steps of this incredible transition. Its whale-like ear bones, specialized for underwater hearing, were already present while its legs remained fully functional for land locomotion. Within just 5 million years, descendants like Ambulocetus, walking whale, would develop webbed feet and tail-powered swimming, demonstrating evolution's breakneck pace when ecological space opens wide. Competing with Mesonychids were the creodonts, mammalian predators so bizarre they seem like nature's first draft of carnivorans. Species like Hyenodon perfected scissor-like cheek teeth that formed continuous slicing blades, allowing them to process meat with terrifying efficiency. Limb proportion studies suggest some species could sustain speeds over 50 kilometers per hour, 30 miles per hour, making them Paleogene equivalents of cheetahs, yet their undifferentiated dentition proved an evolutionary dead end. When true carnivorans arrived with specialized canines and slicing carnassials, the creodonts faded into extinction after 40 million years of dominance. The oceans told an equally dramatic story of reinvention. With mosasaurs and plesiosaurs gone, marine ecosystems became a blank canvas for evolutionary experimentation. Giant flightless birds like Diatryma stalked shorelines, their axe-like beaks capable of dismembering prey as large as small horses. Isotope analysis of their bones reveals these 2-meter-tall predators occasionally supplemented their diet with fruit, a reminder that nature often repurposes existing body plans rather than engineering perfect specialists. Beneath the waves, the first proto-whales were testing aquatic lifestyles, while primitive pinnipeds began their own transition between land and sea. This period witnessed not just physical transformations but cognitive revolutions. Endocasts of early primate brains show the first significant expansion of the neocortex, the region responsible for complex thought and social behavior. Some multituberculate mammals, an extinct group, developed brain-to-body mass ratios comparable to modern rodents, suggesting heightened intelligence. Fossil trackways in Wyoming reveal pack hunting behavior in creodonts, while tooth wear patterns in early ungulates indicate sophisticated parental care strategies. After 160 million years of keeping quiet to avoid dinosaur predators, mammals were finally free to experiment with complex social structures and communication. Climate served as both architect and destroyer of these new worlds. The PETM's intense warming, likely triggered by massive methane releases from seafloor clathrates, lasted approximately 200,000 years, an eye blink in geological time but an eternity for evolution. Carbon isotope excursions in marine sediments show how these conditions supercharged speciation rates. Some mammalian lineages diversified 3 to 4 times faster than background rates. tropical conditions at high latitudes eliminated climatic barriers, allowing species to disperse globally. Fossils of the same mammal species have been found from Colorado to China, yet this hothouse paradise came at a cost. Ocean acidification events during the PETM created carbonate compensation depths so shallow that in some basins even mollusk shells dissolved before reaching the seafloor. By 10 million years post-impact, nearly every modern mammalian order had made its debut. The humble origins of elephants could be seen in Merotherium, a pig-sized creature browsing Paleogene swamps. Bats had taken to the skies, their delicate skeletons preserved in German oil shales. Even the first glimmers of primate intelligence shone through in species like Teilhardina, whose forward-facing eyes and grasping hands presaged humanity's eventual rise. This explosive radiation wasn't due to any inherent mammalian superiority. It was the result of ecological opportunity meeting evolutionary potential in a world reset by catastrophe. The legacy of this period echoes through every modern ecosystem. The asteroid that ended the Cretaceous didn't just kill the dinosaurs, it shattered ecological constraints that had suppressed mammalian innovation for epochs. In the resulting vacuum, these once tiny creatures engineered biological revolutions that would ultimately produce every mammal species alive today, from blue whales to honey badgers to humans typing about their ancestry. The speed and scope of this transformation stands as biology's most powerful testament to what life can achieve when given the chance to rewrite its own rules. A lesson written in fossils and genes across our extraordinary planet. "66 million years later. Why we owe our existence to this extinction. Imagine an alternate Earth where the Chicxulub asteroid never struck. A world where tyrannosaurs continue to rule as apex predators for millions more years, where hadrosaurs developed even more complex social structures, and where mammals remained forever confined to the ecological sidelines as tiny nocturnal insectivores." This wasn't merely a speculative scenario. According to paleontological evidence, it represents the most probable timeline had that 10-kilometer-wide asteroid missed our planet. The cosmic coincidence that wiped out the dinosaurs 66 million years ago stands as the single most consequential random event in Earth's biological history, a fluke of celestial mechanics that made our very existence possible. Recent fossil discoveries have fundamentally changed our understanding of dinosaur biology just before their extinction. Contrary to old theories about dinosaurs being in decline, current evidence shows they were thriving and diversifying up to the very end. In Montana's Hell Creek Formation, paleontologists have identified no fewer than 30 dinosaur species coexisting right before the impact event. Some, like the feathered Dakotaraptor, were evolving sophisticated plumage and potentially more efficient thermoregulation. Others, like the duck-billed Edmontosaurus, show evidence of complex herd behaviors and possibly even seasonal migrations. Hadrosaurs in particular were developing increasingly specialized dental batteries capable of processing tough vegetation, while ceratopsians were experimenting with new horn and frill configurations that likely served both in combat and species recognition. There's absolutely no indication in the fossil record that dinosaurs were losing their evolutionary edge. They remained the undisputed rulers of terrestrial ecosystems until the moment the asteroid struck. For mammals, the impact represented nothing less than emancipation from 160 million years of evolutionary suppression. Before the catastrophe, mammals existed as small, generalized creatures rarely exceeding the size of a modern house cat. The largest known Cretaceous mammal, Rhipinomammus, reached about 1 meter in length and is famous for fossil specimens showing it occasionally preyed on young dinosaurs, but these were exception rather than rule. Most mammals occupied marginal niches as burrowers, climbers, or nocturnal foragers, their evolutionary potential strictly limited by dinosaurian competition. Detailed studies of Mesozoic mammal teeth show remarkably little dietary specialization compared to their Cenozoic descendants. They were generalists because specialization would have made them vulnerable to dinosaur predators. Their warm-blooded metabolism, rather than being an advantage, was likely an evolutionary compromise that allowed them to remain active during cooler nights when dinosaurs were less alert. The asteroid's impact location proved devastatingly perfect for maximum ecological disruption. When it struck the Yucatan Peninsula, it hit a geological bullseye, a thick sequence of sulfur-rich carbonate and sulfate rocks. Geochemical analysis shows this impact vaporized over 100 billion tons of sulfur-bearing minerals, injecting them into the upper atmosphere where they formed sunlight-blocking sulfate aerosols. Had the asteroid hit just a few million years earlier or later, when sea levels were slightly different, it might have landed in deeper ocean waters, where its climatic effects would have been significantly mitigated. The timing was equally improbable, occurring precisely when dinosaurs had reached peak diversity, but before mammals had evolved any significant advantages. The evolutionary aftermath reveals just how contingent our existence truly is. Primates likely owe their origins to the dense, multi-storied rainforests that developed during the Paleocene-Eocene thermal maximum. Fossil evidence from Wyoming shows early primates like Carpolestes developing grasping hands and feet specifically to navigate the complex three-dimensional environment of tropical canopies. Whales exist today because of a unique combination of vacant marine niches and terrestrial ancestors that happen to have the right combination of traits. Mesonychids with their dense bones for ballast and hippo-like creatures with their aquatic tendencies. Even human intelligence might trace back to this event, as primates freed from dinosaur predation could afford to invest in larger brains and more complex social structures. The improbability continues when we examine the details. The asteroid struck at just the right angle, estimated 45 to 60 degrees, to maximize debris ejection into the upper atmosphere. Its composition was just right to vaporize the most climate-altering minerals. The surviving mammals happen to have already evolved key innovations like placental reproduction and lactation that gave them an edge in the post-apocalyptic world. Even more remarkably, the dinosaur lineages that did survive, birds, took an astonishing 15 million years to re-evolve large terrestrial forms like the terror birds, giving mammals crucial time to establish dominance. Had any of these factors been slightly different, had the asteroid been slightly smaller, struck at a different angle, or hit a different part of the planet, dinosaurs might have survived, and mammals might never have gotten their chance. Modern ecosystems still bear the unmistakable imprint of this ancient catastrophe. The nocturnal bottleneck theory explains why most mammals today are still fundamentally adapted for night vision and hearing. We carry the evolutionary scars of our ancestors' forced nighttime existence during the dinosaur era. Our own upright posture and grasping hands represent solutions to ecological challenges that only existed because the asteroid cleared certain evolutionary paths while closing others. Even human childbirth difficulties relate back to this event. The compromises between large brains, which became advantageous in the mammal-dominated world, and bipedal locomotion, trace their origins to the ecological space created by the dinosaur extinction. The philosophical implications are profound. Every human achievement, from the first stone tools to the International Space Station, exists because of a catastrophic event that, had we been alive to witness it, would have horrified us. Our art, our science, our civilizations all stem from a chain of evolutionary opportunities that only occurred because a random rock hit a random spot on our planet at a random moment in geological time. This creates a paradox we still struggle with. Our very existence depends on the type of catastrophic event that we now devote considerable resources to preventing. The same cosmic processes that made us could also unmake us, a humbling reminder of our place in the universe. The dinosaur extinction stands as biology's most dramatic example of contingency. The idea that historical accidents shape evolutionary pathways in unpredictable ways. It demonstrates that progress in evolution isn't inevitable or directional, but depends entirely on circumstance and opportunity. The mammals that inherited the Earth weren't superior to dinosaurs in any cosmic sense. They were simply fortunate beneficiaries of a catastrophe that played to their particular strengths. This insight forces us to reconsider our place in nature, not as the predetermined products of evolutionary progress, but as lucky winners of a cosmic lottery that could easily have had a very different outcome. As we look to the future, this event takes on new relevance. The current anthropogenic mass extinction demonstrates how quickly ecological dominance can shift when environments change rapidly. Just as the dinosaurs discovered, no amount of evolutionary success guarantees long-term survival when the rules of the game change abruptly. The Chicxulub impact teaches us that life is resilient but unpredictable. When one door closes in evolution, another opens, but there's no guarantee what will walk through it. Our responsibility as the current dominant species is to recognize how fragile this dominance truly is, and how much we owe to random cosmic events beyond our control. The same universe that gave us our chance through catastrophe could just as easily take it away. A humbling thought as we contemplate our future on this planet and beyond. Earth after dinosaurs, a post-apocalyptic world that made us possible. For years after the asteroid impact, Earth resembled a nuclear wasteland. The sky remained perpetually gray as fine particles from the impact circled the globe, blocking sunlight and plunging temperatures. Photosynthesis nearly stopped. Forests that once teemed with life became silent graveyards of dead trees. The oceans weren't any better. Acid rain turned waters toxic, dissolving the shells of marine creatures and collapsing entire food chains. This was a planet in shock. Its ecosystems reset to zero. In this hellscape, survival came down to sheer luck and specific adaptations. Small mammals, no bigger than rats, became the unlikely inheritors of Earth. Their secret: they could burrow underground to escape the worst of the heat pulses and nuclear winter. They were generalists, able to eat anything from insects to rotting plants. Most importantly, their warm-blooded metabolism kept them active during the cold years when cold-blooded reptiles struggled to move. The fossil record reveals haunting clues about this period. A layer of fern spores immediately after the impact shows how these primitive plants colonized the devastated landscape, nature's first responders. Above that, a fungal spike appears, evidence of mushrooms feasting on the unimaginable amounts of dead organic matter. Only later do we see the return of pollen from flowering plants, marking the slow recovery of forests. For predators, the rules changed completely. Without large herbivores to hunt, surviving carnivores either starved or shrank in size. This created opportunities for small, adaptable hunters. Snakes, which could go months without food, suddenly found themselves as top predators in many areas. Some evolved to enormous sizes, filling niches left empty by vanished dinosaurs. The oceans told an equally dramatic story. With marine reptiles gone, fish populations exploded in bizarre new forms. Sharks, which had existed for hundreds of millions of years, finally got their chance to dominate. The first primitive whales, still land-dwelling at this point, began their evolutionary journey toward the sea, completely free from the aquatic reptiles that would have competed with them. What's most astonishing is how quickly evolution worked once conditions stabilized. Within 10 million years, a blink in geological time, mammals diversified into hundreds of forms. Some took to the trees, becoming the first primates. Others returned to the water as whales. Many grew to sizes unimaginable during the dinosaur era. This explosion of diversity happened only because the slate had been wiped clean. Had that asteroid missed, our world would look radically different today. Dinosaurs might have continued evolving, perhaps even developing greater intelligence. Mammals would likely still be small nocturnal creatures. The very traits that make us human, our hands, our brains, our social structures, evolved specifically because our ancestors got that one miraculous chance to step into the light. Every time you see a bird outside your window, remember, it's the last living dinosaur, a reminder of the world that once was. And every time you look in the mirror, remember, you're the product of the most unlikely second chance in Earth's history. Don't forget to subscribe, my guest.